Hello everyone, welcome to the third lecture of week 5 of our course on AI for Earth observation. In this week, we are mainly focusing on SAR image analysis, different deep learning problems associated with SAR image analysis. Towards this, in the last lecture, we have discussed object detection architecture called RCNN. Indeed, object detection is one of the important problems in SAR image analysis. It also plays important role in other Earth observation tasks as well, involving the other sensors as well. In today's lecture, we will be taking forward this discussion. We will discuss faster RCNN, and additionally, we'll see a couple of examples related to application of this object detection techniques in the context of SAR image analysis. So with this, let us take our discussion forward. The motivation behind fast RCNN lies in the limitations that we had discussed with respect to RCNN itself. Let us briefly recall how RCNN worked like. We said that RCNN is two-stage detection method, where in the first stage we used, let's say, selective search or any other method to generate the region proposals. Following this, each of these proposals went through resizing and a CNN-based feature extraction, and on top of them we had SVM-based classifiers. So in a way, like, it's not even two-stage, right? In a way, you can think of it as if like three-stage. So we need to somehow work on these different stages so that it starts working end to end. We need to eliminate the redundant CNN computation. That is, if we were generating, let's say, 2000 proposals, we were passing each of these proposals through CNN independently. Instead, can we do better? Can we just run, let's say, once? So this is one redundancy that needs to be accounted for. We need to simplify the multi-stage training, and we need to improve both training and inference speed. So let us see like how we can do this. Fast RCNN solves some of these issues, and some of these issues then get solved in faster RCNN. The fast RCNN, this processes entire image only once through the CNN. It shares the convolutional features across the proposals. It jointly learns classification and localization. Also, fast RCNN is where like we are now going to, we said that okay, like we will omit little discussion on, let's say, bounding box regression and all when we discussed RCNN, and we said that okay, we will discuss this when we discuss fast RCNN. So this is what we will be doing in this lecture. So let us try to conceptualize that how we can go ahead with just one time passing the image through a CNN, that we don't need to pass it again and again for different regions of interest. So here in the picture, what we can see is that given the image, let's say we are processing it through a set of convolutional layers, and we obtained a feature map. Now, at the same time, we still have something like selective search. Okay, so the region proposal generation in the first RCNN, we are still doing independently. And from the selective search, what are we getting? We are getting the region proposals. So this we can think of as if it's working independently. So at one side, from the image, we are using the CNN to get the feature maps. And on the other side, we are using selective search to obtain the region proposals. Here, before going ahead, something needs to be probably made clear is that we are talking about like not extracting feature map from a fully connected layer where it would have lost the spatial information. Rather, it should be from a convolutional layer where we have still retained the spatial information about the features. Now, what we can do is that we can combine these region proposals and the feature maps as if we are doing RY projection, and on the top of that, we'll go for something called RY pooling. Okay, so with this RY pooling, now that we have the features corresponding to each RY, we can now process it through, let's say, fully connected layers. And these RY feature vectors can then be fed to a classifier that is fully connected layers of max, and as well as a bounding box streak erasure, which is in the form of fully connected layer. Now, let us try to think a bit more like how will each of these components work. So, first RCNN pipeline, this comprises of computing the convolutional feature map once, in contrary to what we were doing in the case of the RCNN. We were passing each of these RYs, resized RYs, through CNN. Here we are just doing it once. We are projecting the region proposals onto the feature map. So the region proposals generated separately using selective search or any other appropriate method, this is projected onto the feature map. And then we extract fixed size region features. Finally, we predict the class and the bounding box simultaneously. So the first concept here is the shared convolutional features. Entire image is processed by the given CNN. One feature map reused by all proposals. Thus, we eliminate repeated convolutional operations. So instead of, as I said, that instead of running it 100 times or 2000 times, depending on the number of RYs, we are just doing it once, right? Of course, for the entire image. Previously, it was for each RY separately, each RY is resized. Now, this is for the entire image. But this doesn't really affect the computation, right? Thus, it's accelerating the detection process significantly. Think of running 2000 times versus just one time. So one important aspect here is the RY pooling layer that maps the proposal onto the feature map and then divides the region into fixed spatial bins. So then inside each of these bin, let's say you divide it into, let's say, 7x7 bin, or like whichever way you want to divide this, and inside each of these you can perform max pooling, thus producing a fixed dimensional feature vector. So this is the main aspect, like, okay, from the given feature map, which let's say is R cross C cross B, and from there, and given our like this particular RY, which captures a particular area in that feature map, speciality in the feature map, we want to come to a fixed dimensional feature vector, and this is how this is done. Once we have the fixed dimensional feature vector, then it's quite straightforward. We can process using fully connected layers, and these are shared, of course, all the proposals. Here what we are seeing is multitask learning. That is, at the same time we are predicting the object category. Obviously, as I mentioned before, object category means like we can also assign to the background. So that will be, instead of in categories n+1, and at the same time we are also employing regression to predict refined box coordinates. Joint optimization is happening in single network. Again, try to understand what we were doing in the case of RCNN. We were training SVMs for each of the class, separate SVMs, right? So here it's very different. So the first RCNN loss we can conceptualize as a summation of the two terms, one dedicated to the classification and the other dedicated to bounding box regression. Here we see also two terms, lambda and u greater than equal to 1. So what are those? Also we will discuss soon. Yeah, so what we are looking at, one is P, which we can think of predicted probability distribution over the k+1 classes. So if we are interested in k classes and 1 corresponding to the background, let's say like that is P0 itself, there's a background. U is our ground truth class labels, which means now we can compute using this P and the U a classification loss. At the same time, we have T here, TU, which is the predicted bounding box offsets, the V, which is the target bounding box regression. So again, using this TU and the V, we can now compute an appropriate loss function for bounding box regression. Now, what's happening is that this regression part of the loss function, this is combined with the classification part with this lambda weight or lambda multiplier. At the same time, we also have the indicator function, which is used because the bounding box regression is applied only for the foreground objects. That is, we will be not using it when u is equal to 0. That is, the object, the particular object belongs to the background. In that case, we'll be not using this component of the loss function. Now, talking about the classification loss, we can simply use log loss. And similarly, for the localization bounding box regression, a robust L1 loss is used. Of course, we can also like make your own version with different losses, but this is what was used in the original first RCNN paper and is also followed in most of the follow-up works. So now let us think, did we entirely solve all the limitations related to first RCNN or related to the RCNN family? Let's say like till now, like we started with some limitations with RCNN and we have now solved a few of the issues for sure, but did we solve all the issues? We did not, right? The proposal stage is still not learned. This is still depending on selective search or any other appropriate method, which means the region proposal is still decoupled and slow. So can we do something so that this stage is also part of the just entire architecture? And this aspect was further addressed in the follow-up work, which is known as faster RCNN. So see the sequence: RCNN, faster RCNN, faster RCNN. Faster RCNN acts a region proposal network. RPN can the detector this share the convolutional features. So let us think like how we can achieve this. Towards this, what we're seeing is that given the input image, we have, let's say, the convolutional layers, and from the convolution layers we are getting the feature map, right? Recall what was the case in the case of first RCNN. From the input image we had a parallel branch which we were calling the original proposal generation branch. Let's say it was selective search. In this case, instead, we have this RPN originating from feature maps. Okay, based on these feature maps, we have this region proposal network which generates the proposals, and then these proposals are projected onto the feature maps. So the same thing was done in the first RCNN also, right? In the case of the first RCNN also, the proposals generated by the selective search was projected onto the feature map. Here we are doing the same, which means from this point onwards, we can do more or less like we had done in the case of the first RCNN. The region proposal network is designed to replace traditional methods like selective search. It generates region proposals directly from the feature maps. It operates in a fully convolutional manner. It outputs bounding boxes and corresponding objectness scores. So for this region proposal generation, this objectness score, this is something important. And what we see in the case of this faster RCNN, that this is the main innovation. The other parts, they may remain just the same. So that's not something we want to discuss again. Now that we have discussed the RCNN family, we started with the RCNN. We saw like, okay, how RCNN was really modular. In a way, RCNN is something which is also, from the discussion point of view, it's very nice to discuss like how it is organized into different modules, like every function that's done with different architectures or models which the authors at that point of time thought appropriate. However, I mean, even if it's modular, even if it's like, as I said, like from the academic point of view, really nice to discuss, this had so many limitations, some of which got addressed in past RCNN, and then eventually we saw that some of those got addressed with faster RCNN. Okay, so with this, now let us slowly come back to our discussion of the SAR images itself. And let's say you have a particular SAR dataset for object detection. One possibility is simply apply, this RCNN, faster RCNN, whichever is of your choice, to your corresponding SAR dataset, just as it is, okay? That's quite possible, and not just these methods, these architectures. There could be any other architecture, YOLO and anything else, okay? So that's of course possible. However, maybe we are interested more, to discuss some modifications that probably helps us, to enhance performance, or some modifications which exploit the dataset characteristics of Earth observation, or more specifically in context of this week of SAR images. So we will see a couple of examples where RCNN, fast RCNN, they are adopted with some modifications. So the first example that we are taking is of ship detection with pre-processing steps. The main innovation here is coming from the fact that, considering this particular problem, this particular work, I have also cited the paper in the footnote. If you're interested, you can go through it. So this particular work, what they're doing is they are proposing some pre-processing steps which enhance the performance. I already mentioned before, in the context of marine images, it's quite common that even if it's like whichever type of image this is we're talking about, like whichever sensor, but the ship, this is like will be not captured or not be a part of the entire scene. It depends on the resolution, of course, but generally let's say we're talking about medium resolution images, so ships will be like just few pixels here and there, and the scene will be generally bigger, right? So in such kind of scene, irrespective of sensor, we don't need to think so much about the sensor, at least for this particular discussion in this slide. What happens is that we can apply probably some kind of pre-processing, some kind of morphology analysis and pre-classification, to identify some smaller patches, given a larger scene, some smaller patches which are probably more possible, ships, okay? And given those candidate ROIs, we can also do a appropriate analysis, we can have hog-based analysis or any other kind of analysis to understand the dominant object in that particular, now we have a zoomed in scene, right? So in the zoomed in scene, we can try to understand the dominant object's orientation, and we can correct that orientation to have it in appropriate, if we want all the objects to be vertically oriented or horizontally oriented, whichever orientation we want, we can project it to that particular orientation, and this makes the rest of the processing much simpler. So After that, let's say we now bring in the RCNN. Okay, so this, since all this pre-processing has been done, now applying RCNN on the top of this will enhance the performance of the RCNN or the object detection architecture, whichever we want to use, significantly. Now, the next paradigm that we are going to discuss is semi-supervised SAR target detection. What happens is that CNN-based SAR detectors require large amount of labeled SAR images. However, annotating SAR images is expensive and requires domain expertise. So this is a limitation we have discussed multiple times. This is in general true for Earth observation images in general, however, even more true for SAR images, especially when we think about this kind of talks where we are not just giving a single label to the entire image, rather we are trying to, identify objects within the image. Thus, what's happened is that the large collections of unlabeled SAR images remain underutilized. So similar discussion will be actually coming back again in the next lecture as well. However, this particular time we are discussing more in the context of SAR target detection. So the question that we are asking ourselves is that can we somehow exploit unlabeled SAR images and labeled optical images to improve, let's say fast RCN and fast RCN, whichever. Okay, so can it be done to improve one of this object detection? Let's think end to end. So let's say we are focusing on faster RCN only. Okay, so the another way to ask the same question is also not necessarily we are thinking of transferring knowledge from optical images. We may also alternatively transfer knowledge from, let's say, another type of SAR image, let's say another band of SAR image. Let's say we have actually labeled data set for X band, but we don't have for C band. Okay, so this is also a possibility. It need not be transferring knowledge from a labeled optical data set. It can also be transferring knowledge from a labeled SAR data set of different characteristics. So the next discussion that I'm going to do for next couple of minutes, I'm going to do, assuming we are talking about these two types of SAR images, one which has the labeled images and the other which we don't have. However, the discussion will remain more or less the same, even if we were thinking about the labeled one as optical images. So we have this SAR image type 1, which has the labeled data set, and this, let's say, we are processing it through an encoder, and then the region proposal network and other and output heads and all, and we are getting the outputs. Okay, the output loss computation is happening. So this training, this has labeled data set, we can train this end to end with faster RCNN. Now let us bring in the SAR type 2, which doesn't have the label dataset, or the label dataset size is small, right? So in this case, okay, now we are training this SAR type 2, which means now we are using SAR type 2, we are using the trainable encoder, okay, and SAR type 1 we are keeping a frozen encoder. Okay, now assuming okay, both get fed with similar kind of images, in the sense sensors I'm talking about. So I'm not saying that okay, same image you are feeding to the same, but two encoders, rather the images captured in the similar kind of area. So thus what we are hoping is that they have similar kind of distribution. So the feature vectors we are getting from the SAR type 1 encoder and the features we are getting from the SAR type 2, we want to align those distribution. Okay, on the other hand, with whatever amount of data we have, SAR type 2 can also be, trained with the detection loss as well. On the top of this, what can possibly also can be done is that to probably also further enhance the performance, we can also have a reconstruction decoder which reconstructs back the image, okay, similar to the autoencoder we're talking about, and we can further use reconstruction loss for further enhancing the performance. I mean, at the end, the goal is to, the SAR type 2's trainable encoder to enhance its performance. That's the end goal. Okay, with this, I will end our discussion here. We will continue our discussion about SAR images in the next lecture. Thank you.